Hi there, today on the bench a rare HP vintage device, the HP467A. I was looking for one of their power amplifiers for a long time when this one turned up on eBay. I decided to buy it even though the seller said it was untested. What is this thing? Well, first of all, it's a power supply that can deliver up to 20 volts at up to 0.5 amps. But unusually, its output can do plus or minus voltages adjustable by the front knob. You can drive from minus 20 volts through 0 all the way to plus 20 volts. Even more unusual is that the output voltage can be driven by an input signal that can be amplified. If driven by an AC input, the output becomes an AC power supply, supporting frequencies of up to 1 MHz. In a previous video on the repair of a Solartron power supply, I mentioned that that one can do up to 300 Hz. But since it's a DC supply, the output would always be DC, so at best a sine wave with DC offset. But if driven by a sine wave with 0 offset, the HP467A can output sine waves with 0 offset. But of course, that's just a spec. The big question is whether my unit is working at all, and if not, if I can repair it. The first challenge is the power socket, which uses a long obsolete US standard known as oval connector, or possibly as PH163, and apparently used a lot in the 1960s. I searched for compatible plugs and even power cords, but only a few places in the US were selling them for outrageous money, so forget about that. For a first test to see the status of this unit, I rigged up something scary and hopefully temporary, using crocodile clips and connected it to my current limiting light bulb I showed in the previous video. The problem with wiring like this is that I have to avoid moving the unit even a little, otherwise the crocodile clips in the connector may touch each other or the housing. This is mains voltage we are talking about. Applying power and the light bulb stays dark, nothing explodes or lets out magic smoke. There isn't a blown fuse either, because I heard a relay click and the front light came on, all good signs. However, the output voltage is not correct, so a repair is needed. As with most repairs, I start by checking the power rails, of which there are quite a number. Minus 34 volts is correct, plus 34 volts is also there. Plus 7 volts is reading as 7.4, which is a bit high. Minus 7 volts seem to be completely missing. Plus 15 volts is present, but again slightly on the high side. Minus 15 volts is there, but slightly low. Minus 50 volts is there and also slightly low. I forgot to capture the checking of the plus 50 volt rail, which was correct. If a voltage isn't there or tracked low, a good way to isolate the problem is to remove one by one all consumers of that voltage. In the HP467A there's only one. The minus 7 volts goes as reference into the selector circuit, and to rule out whether a short in that section causes the problem, I temporarily desoldered the wire carrying the minus 7 volt output from the PCB. Measuring the wire's resistance against ground, it's 13.2 kilo ohms, which is exactly what it should be. Certainly no short that would track the voltage to 0. So the problem is with the PCB producing it, not the consumer. And to confirm that, checking the minus 7 volts now that its only load through the wire has been removed shows it's still essentially 0. I used one of my bench power supplies to feed minus 7 volts into the still disconnected wire. This is shown on the left meter. And now the output voltage in the 20 volts setting shown on the meter on the right is at least 21 volts, and it can be adjusted using the front panel knob. It also goes through 0 and negative, but not all the way to minus 21 volts. But it seems if I fix the missing minus 7 volts, most of the rest of the circuitry seems to work, more or less. So there's nothing for it but to remove the PCB that contains the source of the minus 7 volts. It is likely that some component has failed, and for replacing, the PCB has to be out. First, a shielded cable needs to be unplugged, and then a screw holding the board. It should be free now, but the connectors at the bottom are holding it very tightly, and there are no places to really get a grip, so the board comes out only millimeter by millimeter. But once it's out of the connectors, it comes out easily. There are some really crusty capacitors on this board, and one of the pots has some white residue, which makes me suspect some capacitor may have spilled its guts in that area. On the back is an interesting botched RC filter where that shielded cable plugged in. The top of the PCB. I always find vintage PCBs more interesting to examine with all the components in different colors and sizes compared to modern ones which look very uniform and boring on comparison. I concentrate on the area responsible for the -7 volts and start by checking caps with my transistor tester, although testing in circuit is sometimes tricky. This one is for the -15 volts feeding the -7 volts and supposed to be 50 microfarad and seems totally fine. Moving on to the cap next to it, which is the -7 volt smoothing cap, supposed to be 100 microfarad. Let's wait for another measurement, since I moved the probe's mid-measurement cycle. 2.2 ohms and no capacitance inside. Looks like this cap has a short circuit. I desoldered one leg of the capacitor, measured again, and it was still bad. So I removed it completely and tested here, out of circuit. Still a short circuit, so definitely bad. This is a part of the schematics. First, the -50 volts are used to derive the -15 volts reference, which is then used to produce -7 volts. The bad capacitor is C127 and it's completely shortened, basically dragging the -7 volts directly to ground. That load also explains that the -15 volts was slightly low. I measured all other caps and they were still good, yet I decided to get rid of them all. Spray caps have a good reputation for longevity, but I recently repaired another vintage HP device, video coming up soon, which had a similar problem with the spray. Here's a comparison of the bad capacitor on the left with the identical, still good one from the +7 volt rail. It is clear that the black seal at the positive end of the bad one is no longer there. Radial caps are rare these days and expensive, and I only had an axial type 330 microfarads to replace the original 300 microfarads, which requires this bodge. The rest are all replaced with radial caps. The two at the right are pretty big because I did not have a 50 microfarad 50 volt type and used 100 microfarad 100 volt types instead. But since these are smoothing caps, more volts and a bit more capacity is not a problem here. A first test shows about +4 volts output in the 4 volt range. Great! And I can adjust the voltage as expected, and it goes all the way to -4.7 volts, which is a massive improvement. +10 volts seem to be okay, and +20 volts slightly high but present, and I can adjust it all the way down to -22 volts. These are so close that doing a few adjustments may fix this power supply for good. But first I have to sort out the power inlet problem. The socket is riveted in, which means I have to drill the rivets out. Also, there are two 1000 picofarad filter caps from live and neutral to ground and two large inductors taking the power to the rest of the power supply. The modern IEC C6 socket, also known as cloverleaf or Mickey Mouse, is a connector that is close in size and has the needed 3 pins. All I needed to do is to file a small indentation into the enclosure. And it fits. Unfortunately, the mounting holes of the C socket are not usable because they are still in the open area where the original socket once was. I used the original as a template and made a metal plate in which I epoxied the C6 socket after trimming off the useless mounting ears. The connector on the new plate fits and the mounting holes align with the rivet holes of the old connector. As with the original, I added 1000 picofarad filter caps, but because these are between live or neutral and ground, I used Y-class capacitors for safety. If a normal capacitor fails, like one of those used in the old socket, it can shorten live to the enclosure, which may cause an electric shock if you touch it. A Y-class capacitor is designed to fail open, which means it's no longer filtering, but there is no risk of getting shocked. The new power inlet is installed with the two inductors and the green earth wire soldered back on. Connecting the unit to mains is now much easier and safer, and the unit can be moved while powered. I did what the service manual calls a null adjustment, and after that the positive and negative voltages are now nearly symmetrical, although still slightly higher than the nominal. However, it's not clear from the service manual if that's okay. In any case, there isn't a way to adjust them, and since everything else works, I decided to leave it. Now for the interesting part, switching to the amplifier. The calibrator on the left is providing 1 volt DC, well 0.9999 volts to be exact. In times 10 mode this should cause plus 10 volts. And it does just fine. And reducing the gain to times 5 produces plus 5 volts as it should. And switching the input to minus 1 volt in times 5 mode produces minus 5 volts. Excellent. Using a very slow triangle wave from a function generator makes the output go up and down accordingly, which may be better to see on a scope. 10 Hz, about 100 Hz, about 1 kHz, 10 kHz, 100 kHz, and of course I can use a sine wave instead of a triangle. What can you do with this unit, or rather what am I planning to use it for? As a start, I can use it to test the AC amp part of my meters, because getting a stable AC amp at various frequencies is not easy. Here the HP467A is driving 2 multimeters in series through a 10 ohm load resistor. I'm using a frequency of about 400 Hz. Using variable gain, apologies for the focus, I can compare the 2 meters at, for example, 50 milliamps or at 500 milliamps, which is the limit of the power supply. Of course, I can do the same for AC volts, because not many function generators can produce 10 volts RMS. With direct connection I can go up to 14 volts RMS. But since this unit can drive quite a load, I can easily use a transformer as long as the frequencies are low, and boost the output voltage that way. 200 volts at 400 Hz, no problem. Or 250 volts. Or 300 volts. It turns out with this transformer I can go to about 320 volts before the power supply starts clipping. If I use a different transformer I can probably get much higher voltages. Ever since I wanted one of these power amplifiers, I wondered if you can connect a speaker to it. The answer is, of course you can. This is just a small speaker, but that's how 400 Hz from a power supply sound, or any other frequency for that matter. One crucial question remains, can I play music through this power supply? After all, with a frequency range of 0 to 1 MHz, this is possibly the best mono audio amplifier you could buy. Of course it can, although that mini speaker doesn't do it justice. If you like my videos, don't forget to subscribe. There are more projects, repairs and reviews coming up, and it would be great if you decided becoming a Patreon. That would really help this channel. Thanks for watching.